All right, if we look at sampling distribution of a sample proportion, we're taking a sample size that stays fixed, sample size from a large population. Proportion is P, okay? Having some characteristic of interest, let P hat be the proportion of the sample so characteristic of interest might be blue eyes, left-handed, anything like that. Then P hat is the proportion that match that characteristic of interest. The mean is exactly P, or rho, which is the population proportion. The standard deviation is square root of P times Q over N. All right. And be careful, this is only allowed when you have a sample that is the 10% rule, right? This is that 10%. The population is at least 10 times as large as the sample. That my N is less than 10% of capital N. Okay, because it requires some level of independence because we're sampling without replacement. And since we're lacking independence, and this is really a binomial, fixed N, okay, consistent P, and we're counting the number of successes, it is a binomial distribution, and that's why we see this 10% rule popping up again, okay? And I'm also going to show you how these formulas are derived from that binomial distribution. So mu of x is n times p, and sigma of x is square root of npq. And p hat is all my x's, all my successes divided by how many people there were, right? This is counting the number of successes divided by how many gets me my p hat, which is just 1/nth times my random variable x, which is a linear combination. And so what I can do is say, oh, well, that's going to be, if I do 1/nth of x, it'll do 1 over n of my mu of x, okay, which is just 1 over n times np, which is just p. Sweet. So that's why the mean of my p hats should be centered around p, which means that it's an unbiased estimator. Cool. Of p. Isn't that cool? Okay, so unbiased. It means that it hits the mark. My p hat is supposed to measure rho, p, and it does, okay? Sigma of p hats, well, multiplication, remember, when we're doing linear combinations, multiplication affects both, and addition is only mu, okay? This affects both mu and sigma. So we would have 1 over n times sigma of x, which is 1 over n times the square root of np times 1 minus p. Now, if I want to insert this into the square root, I would square it, okay? So I end up with a tall square root np 1 minus p over n squared. And then if I reduce these n's, we end up with square root of p 1 minus p, or q, over n. And that's why that's my formula for sigma of my p hats. All right, so these formulas, you might ask, well, if I have a mean and standard deviation, when can I use a normal approximation? And guess what? It's the same reasons why we had in the binomial distribution chapter, because really, this is a binomial situation, and so all the same rules apply. Except for in this, we were doing the counts of successes. This is the number of successes was binomial. This is the percent of successes. Okay? So they're exactly the same concept, but one we were counting the number of successes, now we're counting the percent of successes. All right? So we can use a normal approximation if the number of successes is greater than or equal to 10 and the number of failures is greater than or equal to 10. And this is the same exact picture that I talked about in the last unit. Here, we can't finish because we hit a wall. Here, we can't have symmetry because we hit a wall. Here, we can't have symmetry because we hit a wall. Here, we can't have symmetry because we hit a wall. Here, we have some symmetry, but we can't actually finish our tails because we hit 2 walls. Okay? Here, we have symmetry almost, but we hit a wall. Here we have symmetry, could be argued, but we're still kind of hitting that wall, okay? Here, seems like there's pretty good symmetry. There's not much in that, so this is that sort of questionable spot. But here, there's definitely flattens out, and we get our normal curve because my NP is 10. There's 10 successes, and my NQ, 10 failures, is also 10. And that's when you really achieve the ability to use normal approximations, NP and NQ both greater than or equal to 10. So let's try a problem. All right. One way to check of undercoverage, and that comes from like non-response error and stuff like that, in a sample, and what they actually do when they're doing polling for elections and stuff like that, is to compare the sample with known facts about the population. So if 11% of American adults are black, or population of adults in a certain city or wherever you're doing your polls, and the proportion p hat of blacks in the simple random sample of 1,500 adults should be close to 0.11. It's unlikely to be exactly, but let's say that the sample contains only 9.2. Notice it's a national is 11%. A national sample got 9.2%. Should we suspect that the sample procedure is somehow underrepresenting blacks? Okay, we could do this by doing an actual just binomial probability, but we're going to do a normal approximation. Okay, so my mean of my p hats should be p, which is 0.11. All right, my sigma of my p hats equals the square root of pq over n, which is the square root of 0.11 times 0.89 divided by my sample size was 1,500. Okay, which comes out to 0.11 times 0.89 divided by 1,500. And then I need to take a square root. That's my variance. If I take a square root of that, we get 0.008. We'll call it 0.0081. Okay? That's where most of my p hats should be around, and this is the average distance of p hats when my sample size is 1,500 away from that. All right, and now we can say, okay, so this is normal, mean 0.11, and we're expecting 0.1181 and 0.19. Okay, when I subtract 0.81 and add 0.81 to both of those. All right. And I can say, what's the probability that I'm getting something less than 0.92? 0.092 is probably way over here, and so I'm expecting a really small probability of being below 0.092. Okay, so I would do normal CDF negative 999, comma, 0.092, comma, my mean, comma, my sigma. Okay. And if I grab my calculator, I can say second distribution, normal CDF, and I'm wondering, negative 999 to 0.092, mean is 0.11, standard deviation is the answer on my calculator, so I'm going to hit second negative, so it's not rounded. Okay, and we get 0.013 is the probability. So the probability that my sample was not underrepresenting this point of the percent of the population, this subgroup, is 0.013. So chances are it was, for some reason, my sampling method was undercovering or not receiving responses from that demographic of the population for whatever reason. And when that happens, what they typically do is they just take their results and they multiply by 11 over 9.2 so that it scales their results. But what it does is it treats an entire subgroup of the population as if they're exactly the same voters, which is not reasonable because subgroups of the population don't all think alike. Okay, so that's one of the major reasons why our polling data ends up being off, is because it's really, really hard to get a good sample. But normal approximations of sampling distributions of p hats. So good luck and farewell.